Good afternoon, dear colleagues. I would like to represent for your attention the report on features of weld metal brittle fracture in Charpy tests. The most important parameter that determines the reliability of materials is the tendency to brittle fracture. Impact bending tests allow to evaluate the reliability of metallic materials. The following criteria are used as reliability indicators. Impact toughness of a standard sample. For example, the value is 40 joules in some standards. The percentage of fiber surface, for example, more than 50%. Also, the use of load displacement curves provides additional information about fracture. At the same time, the criteria usually used for evaluating reliability describe the destruction process as a whole, without focusing on its stages. What is the influence of failure stage on the reliability of material, and what additional information can be obtained from impact bending tests? For example, there are two samples of welded joints made by different methods. Samples have similar impact toughness values. At the same time, a sample with a higher impact toughness has a lower percentage of fiber surface. On the force displacement diagrams, we can register the points of a brittle crack formation. It can be noted that in the right sample, the formation of a brittle crack leads to almost complete destruction and the force on the dynamic curve decreases to almost zero. In this case, almost all of the energy measured in this impact bending test is consumed until a brittle crack is formed. On the left sample, the formation of a brittle crack is followed by a prolonged ductile fracture stage, during which the shear lips and a fibrous section below the area of brittle fracture are formed. While the total energy of destruction differs slightly, the energy spent before the formation of a brittle crack differs by almost 4 times. 12 joules for the left sample and 40 joules for the right. At the same time, the occurrence of a brittle crack in a real structure will lead to catastrophic destruction because the energy reserve in this case will significantly exceed the reserve available in the test machine. Taking into account the observed stages of sample destruction, during impact bending there are different ways the process to be done. The first way, that can be called favorable, is when most of the energy of destruction is spent before the formation of a brittle crack. At the same time, a sample that shows the work of destruction greater than the required limit, for example 40 joules, make the main work until the formation of a brittle crack. This result can be considered as honestly positive. If such a sample shows an energy of destruction less than a certain threshold, then its result can be called negative. Such a sample is rejected. In the case where there is a large proportion of energy spent after the formation of a brittle crack, there may be a situation in which the sample has a fracture energy above the set threshold, while having the energy spent before the formation of a brittle crack significantly lower. When formally classifying such samples as successful, this classification will not be completely honest, since most of the work was done by the sample after the formation of a cleavage and does not affect the reliability of this material when used in real structures. The probability of this situation may differ for a metal with a different microstructure and chemical composition, which should also influence the decision to use this metal in some way, especially for working at temperatures close to the ductile to brittle transition interval. This work was carried out to determine the probability of such a result for various microstructures of low carbon low alloy steels and its welding joints. First of all, impact bending test was carried out for a large number of samples with the recording of load displacement curves. For this purpose, we used the metal of welded joints made by 6 different methods. different electrode composition and welding technology. The steel used as the base metal is 09G2S after quenching and tempering, after normalization, and 17G1S after hot rolling, as well as samples cut out from heat-affected zone of 09G2S joints. Photos of the fracture surface were obtained for all tested samples. Further, all the images obtained were segmented for brittle and ductile parts, and the distance from the notch to the upper border of the brittle part was determined. The sectioning of areas in the image was performed automatically using a neural network created and trained by me for this task. The load displacement curves obtained during impact bending tests were used to measure the displacements at the moment of the brittle crack occurrence, and to calculate the energy spent before and after the brittle crack formation. The analysis of dynamic curves was performed automatically using self-written software. The diagram shows the values of the ratio of energy spent before the formation of a brittle crack to the total energy of fracture, depending on the total energy of fracture. The area colored with gray color includes the results of tests of samples for which the Charpy value exceeds 40 joules, and the work before the formation of a brittle crack is less than 40 joules. However, the most dangerous results are located at the bottom of the chart. It can be noted that the largest number of results that fall into the dangerous area relate to welded joints. At the same time, the proportion of results between the different welded joints is different. To determine the probability with which these dangerous results occur, their number was calculated. At the same time, only those samples that showed the presence of brittle areas on the fracture surface were taken into account. Counting the number of test results that fall into the dangerous zone shows that for some types of welded joints, such results account for almost 25% of samples with cleavage fracture sites. At the same time, the probability of such a result occurring in the base metal or heat-affected zone is minimized. This observation allows us to conclude that the situation in which the values of impact strengths obtained during impact bending tests do not reflect the real reliability of the metal of welded joints may occur quite often. At the same time, tests of the base metal of modern steels with a low sulfur content, such as 09G2S, do not cause doubts about the reflection of the material reliability. Instrumented impact bending tests with load displacement curves can be complicated by the fact that only a small portion of test machines are equipped with the necessary sensors. Therefore, it is preferable to use other sources of information about the destruction to control the cleavage fracture. For example, a suitable source is the fracture surface of the sample. The diagram shows the dependence of the distance from the notch to the top point of the cleavage fracture area, based on the results of analysis of optical photos of welded joints. This relationship is similar for all tested type of welded joints and base metal. Studies of fracture carried out on a scanning electron microscope shows that this dependence is observed at the microscopic level when the length of the initial ductile crack is from 200 micrometers. Using this diagram, the fraction of energy consumed before the brittle crack is formed can be estimated. Also, there is a relationship between the work of fracture before the formation of a brittle crack and the depth of the initial ductile crack. Moreover, this relationship differs for welds and the base metal, which may be due to differences in mechanical properties such as yield strength. The use of traditional parameter, such as percentage of shear fracture, to assess the work committed to brittle fracture is impossible, because the correlation of this parameter with depth of the initial ductile crack is weak, especially in those cases where a high proportion of fracture after the formation of brittle cracks.
The differences in the fracture process observed in dynamic curves and fracture photos are related to the microstructural differences of the tested metal. These microstructural differences are observed in macrophotographs of fractures obtained using a scanning electron microscope. Within the areas of brittle fracture, areas where the crack originates can be identified. These areas at the macro level are surrounded by a large divergent extending part of the relief. Inside such areas, facets are usually found in which the real pattern extends from the center in all direction. Such facets are the places of origin of the cleavage, from which the brittle crack spreads. In the case of a metal that is prone to fracture with a large share of work after formation of a brittle crack, there is a large number of initiation facets, dozens per sample. Moreover, most often, these facets contain non-metallic inclusions in the center. In the case of a metal that is not prone to destruction with a lot of work after the formation of a brittle crack, the number of facets initiating cleavage is significantly less, units per sample. Often, such facets do not contain non-metallic inclusions and are formed either by intergranular destruction or at the grain boundaries. Summing up all the above, we can come to the following conclusions. The metal of some welded joints differs from the base metal obtained by various heat treatment methods, in that it can show a high proportion of work performed after the formation of a brittle crack. Differences in the fracture process may be due to microstructural differences in the areas of cleavage initiation. A large number of possible cleavage initiation points leads to the formation of brittle cracks in the early stage of fracture. At the same time, a metal with such an increased content of cleavage triggers must have a high resistance to the propagation of a brittle crack, which is reflected in its stopping and subsequent ductile fracture of the remaining sample section. Because otherwise, it would not have met the formal requirements for reliability in terms of impact toughness and would not have been included in this study. At the same time, a metal with a small number of triggers is cleavaged at the later stages of loading, but its microstructure does not have a high resistance to the growth of a brittle crack. It seems that the ideal case will be the simultaneous small number of cleavage triggers and the high resistance to the growth of a brittle crack. The reasons why these properties are usually not combined in welded joints of low alloy steels will be the further direction of this research. Thank you for your attention.